So capture, mark, recapture, or CMR data is one of the most important data sources for parameterizing population models. It can estimate, based on CMR, capture, mark, recapture data, we can estimate survival, variation in survival, lambda, recruitment, dispersal rates. We can estimate pretty much everything we need for our population models. Everything we've talked about in this class that has to do with modeling populations from abundance to per capita vital rates, we can estimate it using capture, mark, recapture data. So it's definitely worth talking about, and that's what we're going to get into in this mini lecture. Capture, mark, recapture is a type of statistical analysis. Now, of course, this is not a statistics class, but let's just quickly review what we're doing. When we do statistics, we're interested in estimating a parameter, right? And that's what we're talking about today, parameter estimation. So we're interested in estimating parameter for a population of individuals. Now, here's the population. So the parameter is relevant to this population, or we're trying to model this population, and so we want the per capita vital rate, the per capita birth rate, say, for this entire population that we're interested in, all right? And the problem is that we can't observe all the individuals in the population, and this is generally what we're doing in statistics. Is we have a population about which we want to make inference. We want to estimate parameters for this population, but we can't observe the whole population. All we can do is observe a small subset of the population, and that is called the sample. So we take a random sample from the population that represents the population to the best of our ability, but is not the full population. We can then take a sample of individuals. In this case, our population is composed of individuals. It's a wild animal population, but this population could be anything. It could be, the all humans on Earth, or all males, or all Americans, or it could be any population of interest. We're using the term population very generally, but in this class, we're actually talking about a real population of animals. So we take a sample of those individuals, and we compute statistics on that sample. A statistic is some transformation of or some data collected on a sample, and some summary statistic or summary of the data from this sample. So we might record the height of every individual that we sample, and then a statistic would be the mean height of our sample, right? The sample mean is a statistic, right? So we have a population that might number in the millions. We have a sample size of, say, 75, and we get the mean height from all the individuals we sampled. The sample mean is called a statistic. And then the key in the field of statistics is then going from that statistic to making inference about a parameter that is relevant to a much larger population. So we take a statistic that's only describing a sample, and then we use this arrow here is really representing the field of statistics, where we go from a statistic that just describes a sample to a parameter that describes a whole population, right? And so that is what we're doing in mark recapture analysis. We are taking a sample from a much larger population, and we're computing statistics. For instance, the mean survival rate, or the mean fecundity, or whatever we want out of the sample. But then we can make inference about a parameter that describes a much larger population. So that's what we're doing. And you'll have more experience with this if you complete Lab 7, which I encourage you to do. PVA parameters that you can estimate from capture, mark, recapture data, again, include pretty much everything that we've been talking about in this class so far, including survival, fecundity, recruitment, abundance, and dispersal rates. So the data needed for capture, mark, recapture analysis is basically just a set of capture histories. This is what the data look like when we do a capture, mark, recapture study. So basically, again, a capture, mark, recapture consists of a group or an individual surveyor going out and surveying a wild population, capturing as many individuals as they can capture, and marking all new individuals with some a unique identifier, whether it's a pit tag or a collar or an ear tag, and then going out again and again, year after year, and again capturing as many individuals as they can capture. If it's a new individual, you give it a unique mark. If it's a recapture, you record the existing mark so that you can then summarize your data in something that looks like this. Now imagine that we are monitoring a population of alligators. All right, these alligators were monitored for 4 years, from 1976 to 1979. And each row represents basically a unique capture history. And what do I mean by a capture history? What we have is one represents, yes, an individual was captured, right? So this individual here was captured in 1976, 1977, 1978, 1979. But some individuals are not captured in a given year. So this individual happened to be captured in 1976, but it was not seen in 1977, and then was seen again in 1978 and 1979, right? There's this final column represents the number of unique individuals that share a common capture history. So in this case, we have 6 individuals that were not captured in 1976, were captured and marked in 1977, and then recaptured in 1978 and 1979. And then we have 5 individuals that were first captured in 1978, and so on and so forth. So there's lots of different types of capture histories that are possible, right? You can have not captured, captured, not captured, captured. You can, have any combinations of zeros and ones that you can imagine. And there's also, in some cases, capture histories also consist of this designation 2. And a 2 represents an individual that was captured but not released. And usually what that means is that the individual died upon capture or in handling the individual. Okay? So not captured, not captured, captured but not released. And so then, of course, it's 0 because that individual was never released back into the population, so it would never be captured again. So the final is 0. Everything after the 2 has to be 0. So this is how we can arrange the data for a capture, mark, recapture, or CMR study. All right, and we'll have a chance to play around with it. We'll do a demo in just a few minutes. But first, there's a couple major types of capture, mark, recapture analysis. They're called closed population models and open population models. Closed population models make an assumption that the population is closed to all bide processes. That is, there's no births, there's no immigration, there's no deaths, there's no emigration, which means that since those are the only flows that can change this total stock of the number of individuals, the total abundance, the abundance is constant across the study. What does that allow us to do? Well, first of all, it allows us to ignore all the bide processes, so we don't have to think about births, mortality, immigration, emigration, right? So the only thing we really can estimate in these models is abundance. So when you see closed population models, it means we're trying to estimate abundance from capture, mark, recapture data. And that's an extremely important thing to do. And that's a lot of times exactly what managers want to estimate. They want to know how many individuals are in the population. That's such an important parameter to estimate. And that's why there's a whole set of methods just designed to estimate population abundance. And those are called the closed population models. And the most simple closed population model is called the Lincoln-Peterson or the Peterson method. All right. So what we do in this Peterson method is we just have 2 surveys. In this case, we don't even need to use unique markings. All we have to do is be able to mark individuals in a way that we can distinguish marked individuals from unmarked individuals. That's all that matters. So in the first survey, we go out and we catch several animals. We catch as many animals as we can, and we mark them all. All right? And the number of marked animals that we are able to capture is termed M. We call that M for marked. We return all those animals to the population. We let them back, and ideally they'll just mix back into the population. And then in the second survey, we again go out and catch as many animals as we can. That number of animals is C. So that's the number of individuals captured in the second survey. And some of those individuals were marked in the first survey. Those individuals are counted towards recaptures. Those are called recaptures, and we term that R. So we have three different summary numbers that we get out of this two survey method. We have M, the total number of individuals captured, marked, and released in the first survey. And then we have C, the total number of individuals captured in the second survey, and R, the total number of those individuals that had been marked previously, and therefore they're called recaptures. And we return those animals to the population. So that's the full methodology for the Lincoln-Peterson method. Let's go through how we will estimate abundance. This is a type of closed population model. And so again, we're trying to estimate abundance. And so we have, what do we know? Well, we know M is the total number marked in visit 1. All right. What else do we know? We know C, total number captured in visit 2. And then we also know R, the total number recaptured, I'll say, just recaptured in visit 2. That's the total number of individuals that had been marked in visit 1 and were recaptured in visit 2. So R is always going to be less than or equal to C. All right? So we can make an assumption here. What we're going to assume is that the ratio of individuals that were marked in visit 2, that is R over C. So we go at that C is the total number captured in visit 2, R is the number of those that are marked, right? So the total proportion marked of the sample that we captured, that we caught in visit 2, we're going to assume is equal to the total fraction of individuals marked in the whole population, all right? So N is the population abundance. That's what we want to estimate. So that is total population abundance. All right, that's what we're doing this for. So all we have to do now is refactor this equation to solve for N. So first we can just flip these things over and just say N over M is equal to C over R, right? And if we just move this up a little bit, we can then compute N is equal to M times C over R, which is the Lincoln-Peterson formula. And we can put a little hat there to indicate it is our estimate of population abundance. Now, I should mention that this here is a statistic. So what we've done is we've collected a sample of individuals that we could capture. We didn't monitor the whole population. We acknowledge the fact that we can't see all the individuals in the population. So we get what we can. We get M, C, and R, just like that's what we happen to get. And we can compute this number N hat, which is a statistic. So what we would like to do is to be able to make inference about the whole population and say, this, this is what we know about the population. This is what we know about abundance. Now, think about this. We could run this experiment again, right? We could go out, visit one, we collect however number of individuals we can capture, we call that M, and then we go out again and we capture a bunch of individuals and we count the fraction of them that are previously marked. Would we get the same answer? Would n hat be the same? Probably not. Just by random sampling variation, we'd compute a different n hat, right? But it's the same population, and we could do it again and again, and every time the statistic would be a little different. N hat would be a little different. So in order to make inference about the larger population, what we have to do is to have some information about the sampling variability. How much will it vary every time we do this experiment? Every time we, go out once, mark individuals, and go out again and count the number of recaptures, it's going to be different every time, but how different is it going to be? So what we can do, imagine we can say, okay, let's say that n hat, after we do this, is equal to, so n hat is equal to, let's say 71 individuals, right? But again, like we said, it can vary, right? So what we can go further and say, we know something about the sampling variation, 71 plus or minus 5. Now we can make inference about the population. We acknowledge that every time we do this experiment, it might be a little different, but we know that the true population abundance is probably somewhere between 76, right? 76 and 66. So we should be able to, that's what statistics is all about, is being able to make inference about a larger population and say, this is what we really know about the true population. So it's not really a statistic until it has this sampling variation attached to the statistic, which gives us an idea about what we really know about the population of interest, because we could care less about the sample. We want to know about the population. All right, let's go back to the lecture. Again, this is our Lincoln-Peterson formula, right? And in lab, which is optional, you will have a chance to run a more sophisticated closed population estimate of abundance that doesn't just have 2 visits or 2 surveys, but has multiple surveys, and it's a much more robust estimate of abundance, and it's called the Schnabel estimator. All right. Okay, we said there's 2 types of capture, mark, recapture estimates of, first of all, we said that, we can compute lots of things from capture, mark, recapture data, survival, fecundity, recruitment, abundance, lambda, all that stuff. But when we used closed population models, all we could do was estimate abundance. But how do we estimate all these other things? Well, that's where we have to use what's called open population capture, mark, recapture models. Open population models allow for the population to change over time due to one or more of the BIDE processes: births, immigration, deaths, emigration. Abundance can change, and we can estimate the change, and we can estimate the processes that are causing the change, like birth rate, death rate, and possibly migration rates. We can do that with capture, mark, recapture data using open population models. And the results from these open population models, the survival rates, birth rates, are often of great interest to ecologists and managers. We can learn a lot about populations from open population models. Now, to understand what's going on within open population models and how we make inference from the MarkRecapture data, how we infer survival rate and birth rate and that kind of thing, well, we have to know that there's a type of inference method called maximum likelihood. It is not something that I need you to fully understand as part of this class, because it's a pretty advanced topic, and it's not a topic that even intro stats classes will get into with much detail. But I just want you to know that this is what's going on behind the scenes when you run ProgramMark, probably the most common software engine for running capture, mark, recapture analysis, or when you do the similar types of analyses in R. what it's doing behind the scenes is called maximum likelihood estimation. I'll give you just an example from MarkRecapture data, because I do think you can understand. It's not that crazy difficult a concept. I think you will be able to understand it if we go through a simple example. So let's think about this example now. We have an open population model, and let's assume there's no immigration and emigration. There's only, in fact, there's no births either. What there is just a chance of mortality. There's a survival process here. Okay, so we're going to try to estimate survival from MarkRecapture data. All right. So let's imagine or consider this capture history. This capture history represents a single individual who was captured and marked in the first survey, was not captured in the second survey, was captured in the third survey, and captured in and recaptured again in the fourth survey. All right. And we're going to try to estimate the probability of survival from this type of data. But first we have to build a model that describes what the probability of these data actually are. And we have to think about the processes that go into making this data happen. Well, let's think about a couple things before we even get into the equation here. What do we know about this individual? Well, one thing we know is that this individual didn't die, right? Because you might see this 0 here and say, well, maybe the individual was not captured, but maybe it died, right? But we can exclude that possibility because we know that we captured it at a later date, right? So it couldn't have come back to life. That doesn't happen. So we know in this case, this individual was alive, but we missed it. We just didn't see it, right? All right. So when we think about the processes behind these data, what we do know is that, we captured this individual, we failed to capture a living individual, and then we captured and recaptured that individual again. And so this individual was marked and released on initial capture, and we can say that the probability of observing this capture history, right, is equal to, and let's just assume that we already know the individual is in the population, right? So we know that the individual survived in this time period from time 1 to 2, but it was not seen, right? So the probability of this segment here is the probability of surviving from time 1 to 2 times the probability of not being seen at time 2. What about this transition? Well, this, we know that it survived, right? Because we were able to see it. So the probability of surviving times from time 2 to 3 times the probability of being seen at time 3. And when I say times, it just means and, like it both survived and we saw it, right? And here again, it both survived and we saw it. So we can multiply those probabilities, probability of surviving and probability of being seen. So that's how we can kind of think about how likely or what the probability of this particular capture history is. And we can write that down in an equation. So the likelihood of this capture history is equal to this is phi, the probability of surviving from one time step to the next. And this is p, the probability of being seen, the probability of being captured at any given survey, okay? And so 1 minus p is the probability of not being seen, right? So this is survived and was not seen. That represents this first interval here. And then survived and was seen, phi times p. And then survived and was seen again, right? And so this is the likelihood of this capture history, all right? Now we can look at a different capture history. This is 1, 0, 1, 0. So this individual was captured, marked, and released. And then it was not captured. Then it was captured again. And then it was not captured. And so let's think about the probability of generating this data set. What does it take to generate this data set? Well, you have to Just like before, you have to survive. We know it survived because we saw it again in the future. It survived and was not captured. So we already did that. We know what that means. Now, what happened here? Well, it survived. We know that, and it was captured, right? So that's the same as we had before. But when we look at this transition here, we don't know that it's still alive because we don't know. We don't have any future occasions where it was captured. So down the road, we don't know. This individual could be dead, or it could be alive and not captured. There's two possibilities. So it either survived this interval and was not captured, or it didn't survive at all, and of course was not captured because we assume we're not going to be able to capture dead individuals. So we can actually write this out. We can say, okay, this individual survived and was not captured. That represents that second 0. And then it survived and was captured. That represents that third 1 in the capture history, right? And then it either survived and wasn't captured, or it died, all right? And this is how we represent it using probability calculus. And you don't have to understand that, but that's what we're doing here is we're saying, okay, the probability of this capture history can be written like this, all right? So now let's quickly just ask the question, if survival was 100% and capture probability was 100%, what's the probability of observing these above capture histories? So let's imagine we have these two capture histories. We know this is what we got. We did go out in the field and we captured these two individuals. If survival and capture probability were 100%, what's the probability of observing this capture history? Well, if you answered 0, you're right, because if capture probability is 100%, you'd never see zeros. And if survival rate's 100%, you'd never see zeros. So neither of these capture histories are possible to observe if the probability of p and phi in these equations are equal to 1. You just couldn't observe. So in maximum likelihood estimation, what we do is we just tweak these parameter values. We just, by trial and error, let's say, okay, so obviously 100% for capture probability and survival that's not possible. But what if capture probability were 75%? Well, in that case, we could rerun this and say, well, that is possible here. If capture probability is 75%, we could definitely observe this data, right? And we can just keep on playing around with it. What if capture probability was 85%? What if it was 50%? What if survival was 75%? What if survival was 90%? And we find the values of phi and p, survival rate and capture probability, that maximize the probability of observing the data. That's what maximum likelihood is. It's just kind of an educated guessing system where we take the parameters that we're interested in and tweak them until we get the values that maximize the probability of our data. In this case, this and this. All right. Now, if you didn't understand everything there, that's not terrible. These are really advanced topics, and this is not a statistics class. But just know that this maximum likelihood. This is what's going on under the scenes when you run something like ProgramMark, or when you do similar analyses in R. All right, and that's what we're going to do in a second with a little demo. So basically, ProgramMark is just an engine for running maximum likelihood estimation to estimate key parameters like survival and abundance from MarkRecapture data. All right, so that's what ProgramMark does. ProgramMark, let me just briefly say, is a free software that's commonly used to estimate population parameters from MarkRecapture data. It is a Windows software, so it is not, you can't really use it on a Mac unless you use one of those Windows emulators. Not going to belabor the point, but ProgramMark is also a little clunky. It was written, decades ago and is not the most user-friendly software. I'll just say that. And now at this point, there's so many ways to do similar analyses in R that many researchers are moving away from just using ProgramMark and are computing parameters in R. And NRES 488 was almost entirely a ProgramMark class until just recently, all right? But things are changing a little bit, and now NRES 488 is taught mainly in R. And they don't really use ProgramMark much anymore. It's useful to know what it is, and it still can be useful to run through some demos. Just make sure you know how to use it, but it's not as critical as it once was in the wildlife profession. All right, let's run through an example of a MarkRecapture analysis. When I say CJS, I mean what's called, it's a type of open population MarkRecapture analysis called Cormick-Jolly-Sieber, and it's the most basic type of model that ProgramMark runs, and it's really the most basic open population MarkRecapture analysis. It's just like what we were doing before. This is the likelihood of a Cormick-Jolly-Sieber model, basically, and all we can estimate from it is phi, or survival rate, and capture probability, right? So these are the only parameters that we can estimate from a Cormick-Jolly-Sieber model, because we are only modeling survival process. We're not going to model birth or recruitment or anything, or immigration, emigration. So what we're going to do is we're going to do this basic Cormick-Jolly-Sieber model where we're going to try to estimate survival rate for European dippers. And European dippers, why European dipper? Well, it's just the most common open population demo. For whatever reason, it's the classic example of a Cormick-Jolly-Sieber model for estimating survival rate from MarkRecapture data. So we're going to do it just because that's what everyone else does, and we're not creative enough to do something different. But here's a picture of the European dipper. Let's go into R. So what I encourage you to do is to load this script. So go to, you can just save this script wherever you would like to save it, and go into RStudio and load it up. It should be called lecture15.r. So I'll just load it up again just to show you. There you go. Load up the script. If you don't already have the marked package, then install it. So you can just go to install and just load up a package called marked. And whatever, I can restart R. I already have it loaded, but I'm just illustrating what you would do. So hopefully you can install the package if you don't have it already, and then you're ready to go. Like many packages, the marked package has data built in for testing. And one of the data sets that marked has is called dipper, and that represents a MarkRecapture data set for the European dipper. So first of all, let's load up the library, all right? And then let's load up the dipper data. And so once you use that data function, you'll see that the dipper data becomes loaded into your global environment, your workspace. And we can look at it. If we type out dipper and hit enter in the console, or if we highlight the word dipper in our script and hit control enter, we get to see what's actually in the dipper data. And this is what it looks like. We have capture histories representing zeros and ones. See that? Every row represents a different individual, and every element within the capture history for each individual represents a different survey or a different year, right? So this individual happens to be not captured. It actually wasn't captured until the 5th survey, and it wasn't seen again after that, right? Whereas, here's some individuals that were captured on the 6th occasion and then captured again. And there's also information about the sex of these individuals, all right? So males and females. So that's the information we have for these dippers. And what we want to do is estimate survival rate. And we can estimate survival rate by sex if we want, because we have the information for males and females. So first of all, we're going to use a helper function from the marked package called process data. That's just going to help us to process the data and get it ready for analysis. All right. Same with this make design data function. It's just all it's doing is processing the raw capture history data into a way that's going to help with the analyses down the road. So we're just basically, getting the data ready for estimating survival. Next, we can actually fit some models. All right. Here we're going to fit a model. Let's see, this one is called, this is going to be time varying. So what we're going to do is we're going to allow survival rate to vary for each time period. We're not going to assume that survival is constant. We're going to let survival rate vary. What does that imply to you? It's like environmental stochasticity, right? We have variation in survival rate with time. So what we're going to do here is fit a model that we could use to generate environmental stochasticity estimates. So let's run that model. And we just did it. So if you run that line, you've run your first, unless you've done it before, you run your first capture, mark, recapture analysis. It's that easy, just like anything. R makes it pretty easy if you know what functions to use. All you have to do is use this function CRM, which is from the marked package, give it the data, and tell it what model you want to run. In this case, I'm running the time-dependent model. So it knows this, tilde time syntax just means run the model with separate estimates of survival and capture probability for each time period. All right, and you give it some methods. And that's great. That's all you need to do to run this model, and we can look at the results. Oops, I didn't actually run it because my system errored. So I'm going to rerun everything up to now and run the model. And I can look at the results. And as you can see, what I get is a separate estimate of survival rate phi for every time period, right? And the same thing with the estimates of capture probability. Now, you might notice that capture probability is above 1 in this case, and survival rates are less than 0. That doesn't make sense to you, right? Well, the thing is, when they do these estimates, the estimates are actually on a different scale. It's not on the probability scale. It's on the logit transformed probability, which can go from negative infinity to infinity. So these actually, don't worry too much about that, but these are actually, realistic numbers. And we can also extract what's called the AIC from this model, and that's going to help us compare this model with others if we want to determine what the best way to model survival rate is. If maybe a constant survival rate model fits better than a model with survival rate varying by year. So we might want to do model selection. AIC is a way that we can determine what the best model is, and specifically we pick a model that has the lowest AIC. All right, that's the best model. We can fit some different models. This time we're going to fit a time invariant model. That is, we're going to make survival rate constant and capture probability constant. All right. And we can look at that model and we can see that there's only two estimates, one survival rate and one capture probability. And we can get an AIC for that, and we find that the AIC is indeed lower for that model. So this is actually a better model than the model with time dependency, all right, with separate estimates for each time period. We can model it by sex, right? We can model survival by sex, and now we get separate estimates of survival and capture probability for each sex. And that has, again, not quite as good a AIC score. It's a little higher. But we can run any type of model we want. In fact, we can set up a whole bunch of different models. That's just setting up a bunch of different models that we want to run. And then we can run this whole wrapper. This wrapper basically, what it does is it runs all the models that you've already specified, right? So we can run all those models in one fell swoop just by doing that, but I forgot to run this line. Now I can run all the models. And it takes a second, but we're running a lot of different models. All right. And now we can look at a table that the marked package creates for us, which tells us which model is the best. And we can see that in this case, the simplest model is actually the best model. It's the model with the lowest AIC score, and in this case, it's the best model. All right. We can then, get the parameter estimates for that model. All right. We can plot out the predictions if we want. We're going to make predictions and plot out. Let's see. Oh, so I'm going to take the model 11, which is the time-dependent model, and I'm going to look at the phi estimates, the estimates of survival rate by time, right? So here I can see that I have different estimates for each time period, right? And if I want to plot them out, I'm just going to plot out the estimates. That is the survival rate estimate for each time period, right? And I can also put error bars on them because, as you see in this phi by year, there's also, phi by year, there's also confidence intervals, a lower bound and an upper bound on those survival rates. Remember, if I took a different sample, if I went out in this population and took a different MarkRecapture sample, I'd probably get different estimates, right? What I want to see is error bars. If I'm going to make inference about what the true survival rate is for my population, I can't just end with just points here. They have to have error bars. So let's add error bars to represent statistics. This is making inference about the population. And see, we really can't get much out of this first year of survival data. There's a lot of uncertainty. In fact, it's almost maximized from 0 to 1. We really know nothing about survival rate. But in the following years, we do have some information about survival rate. And we have some limited evidence that survival rate's higher in the first few years and lower in the second few years, in the next few years. And then the final thing I want to show you is if we can compute the mean survival and the standard deviation in survival, which could go into our model as environmental stochasticity if we put a normal distribution, a normal random number generator on per capita survival. The mean is 0.58 for our European dipper population, and the standard deviation is 0.1, which is what you would need to parameterize a normal distribution for survival rate. So that's a very quick first pass through an open population capture MarkRecapture analysis using the R package marked. In the optional lab, you can go through ProgramMark as well as doing some more sophisticated things with the marked package in R. I encourage you all to do the lab. If you can, I think you'll get a lot out of it, and you'll be in better shape to go into NRES 488. So please do that and let me know if you have any questions. And anyway, hope you're all doing well. Have a great rest of your week, and I'll talk to you soon.